Welcome to Inner and Outer Worlds.
Okay, welcome back, guys, to another episode of Inner and Outer Worlds podcast. I'm here with my boy, Zaki.
Hello.
Okay, and today we're going to be talking about science again. So we're hitting you with the double whammy.
Science.
Actually, no, we did separate it with the 5MEO
Trip
episode.
report.
Yeah,
Good.
so not quite a double whammy. It's like a 1.5 whammy. This one's going to be a bit more scattered. We're just going to talk about cool science shit. I've got some stuff I want to explain, and then Zach's got some questions that he's interested in. We're just going to have a little banter here and have some fun.
Science.
How you feeling, science man?
Good. You're the science man. Tell me all about it.
Okay. So, I'm just going to paint a little picture for you, Zach. You probably know this stuff, but we'll see. You can ask questions along the way. I'm just going to give like a big, broad overview. I'm not really going to get too much into intense details. But what I want to explain is sort of like how we find ourselves where we are in this universe, like in our galaxy, and with a sun that's shining and burning fuel and giving us energy and stuff. And I'm not going to get into too many specifics, but let's just paint like a broad picture. So where we start with this is we can say we start at a Big Bang, but like that's complicated. So we won't get into details there, but let's just say the Big Bang happened. There's a bunch of energy and light and like some particles bouncing around, but it's really hot. So there's not like anything like formed, like there's no like planets or anything yet. It's just really hot, like gas left over by the Big Bang. So it's just like this big bundle of hot particles and light just bouncing around. So that's kind of like what the state of the universe would have been at some point in the past.
Pause. Does the heat cause it to expand outwards, or just the bang was so powerful off the start that's what it caused it to go outwards?
So it's kind of like the expansion of the universe is kind of a tricky thing to understand, because it's like literally the expansion of space itself. So like what you can think of is like all of the space that we're used to around us. Like I can walk from the side of the room, like at some point all of the space in the universe was like contained in a single point type thing. So like the space itself is expanding out.
So crazy, man.
And accelerating in its expansion, which is also tricky to think of. You can think of expansion of space as like if you have a balloon and you tap like 2 points on it with a Sharpie, and then you blow the balloon up, then those points expand away from each other. So that's kind of like you can picture any 2 points in space as like expanding away from one another on a large enough scale. But okay, so we have a bunch of hot gas, and if you know a little bit about matter, matter likes to attract to itself. So if you have any two bits of mass somewhere in the universe, they'll have some like gravitational pull towards one another. So over time,
mass didn't come around for a long time though, right?
Well, mass was produced in the Big Bang.
Oh.
And there's just like light and like fundamental particles, basically. Like there'll be like some protons and electrons and stuff, just like in
right
this big soup of space. And they're going to be really hot. So this gravitational pull for a long time doesn't really like get particles to bunch up together. But over time, on average, you'll start to get like these clusters to start forming. So basically at all times, the universe is expanding, it's cooling down, which means that there's more like space for these particles to move around, and eventually they'll like start to like lose some of their energy, and then this gravitational force can start to pull them together. So you start to get like clustering or aggregation of mass. So you start with this just like hot gas.
Which is too hot for gravity to pull it together.
Yeah, exactly.
Okay.
So eventually you start to get these particles, which are like just like protons, electrons, and stuff. Basically like hydrogen gas, because hydrogen is just a proton and an electron. And those start to like become attracted to one another and to start clumping into like little clusters everywhere in the universe. And then there's motion and stuff, so it's quite complex, but eventually these clumps of hydrogen gas can start to pull enough other particles together, and then once you have a big mass formed, then other nearby particles will want to clump in, so you get this like runaway clumping of matter throughout the universe. And I'm skipping over lots of details here, but essentially what I'm describing is stellar formation, or like stars or suns start to form here, which are just big clumps of hydrogen gas.
No helium's required for that?
No,
For a
no,
star?
no helium will exist at this point. Like, okay, maybe a tiny bit from like the Big Bang, but even then, I don't think that's necessarily the case. It'll mostly
Trace
just
amounts, if any.
Yeah, if any. So I'm going to describe how helium comes about as well. So you get this clumped up hydrogen gas. Eventually, once you get enough hydrogen gas in one space, it gets really dense and really hot. And I'll just describe like the electromagnetic interaction quickly. So if you have a proton, which is at the middle of the hydrogen atom, and another proton, which would be like another hydrogen atom. So protons are positively charged. So if you try to push those two together, they don't want to be together. They're going to fly off in other directions. And so you'll get these clumps of hydrogen gas and protons, and they'll just be like bouncing around. They're not going to do anything. They're just going to be bouncing all over the place. They're going to want to stay away from each other, but you're getting this clumping of gravitation, pushing them closer and closer together, making them really hot and close in space to one another. And they're going to be bouncing really fast. And eventually, once you get enough mass all in one space and enough energy of these particles, they're going to get close. And they're going to get so close, in fact, that another force starts to take over, and that's called the strong force. So there's 4 fundamental forces in physics. I've described 2 of them already. The electromagnetic, which is this pushing away of protons, and then the gravitational force, which is pulling everything together. And then there's another force called the strong force, where if these 2 protons get close enough, they can start to exchange what are called gluons. And those are really sticky. So hence the name gluons. So these gluons start to stick these protons together if they get close enough. And that's the process of nuclear fusion. So basically what I've described is you get all this random hydrogen gas everywhere. It starts to clump into what you'd call like the like a protostar, like the formation of a star. And then eventually it gets hot and dense enough that you get this nuclear fusion process happening, which is the sticking together of these protons. And once 2 protons stick together, that releases a lot of energy. And 2 protons won't want to stay together because there's still the electro-repulsion. So most of the time, those 2 protons will just snap away from each other eventually. But there's another force, the 4th force of physics, the last force, called the weak force. And this force can turn protons into neutrons, and it can turn neutrons into protons.
Wow,
So,
I didn't know that.
Yeah, so that's at the process of radioactive decay, which I'll explain later in this episode.
Sorry, protons into neutrons and?
and then neutrons into protons, depending on situations. So these two protons snap together. Most of the time, they'll just fly apart quickly after because they don't want to be together because they're positively charged. But if the weak force can engage quickly enough, one of those protons can turn into a neutron. So now you have a proton stuck to a neutron, and that's relatively stable. So that's called deuterium. So it's a proton and a neutron stuck together. Then you can have another proton fly into that. And you can start to get like these clumpings of protons and neutrons together. And eventually, with enough collisions and clumpings, you can form helium, which is 2 protons and 2 neutrons. So this is the process that's going on in the core of every sun and in our sun. This is like the main energy production mechanism of our sun, which at the core of the sun, it's hot and dense enough that you get a crap ton of these interactions happening, these fusion events, and those are creating even more heat. And it's causing, like, we talked about chain reactions at some point, possibly in the science episode before. I don't remember if we quite talked in much detail, but
you can go in detail here.
Yeah, essentially, you go from like hydrogen gas everywhere in the core, and then these hydrogen atoms, but it's really just the protons we think about, because it's so hot that hydrogen isn't even able to be like stable. Like, for instance, a hydrogen is the electron orbiting a proton, but it's so hot in the core of the sun that we call it a plasma, where they're not quite able to form atoms. So you just get like a soup of electrons, protons, and stuff. So at the core of the sun, you get these fusion events. And we call this like burning. So our sun is burning hydrogen, but it's not burning in like any normal sense of burning. Like, it's not like when we make a fire with combustion. Like, that's what we would call burning. But this is like a nuclear burning type thing. So it's burning hydrogen gas in a fusion process where it's fusing protons together, eventually creating little helium nuclei. So our sun's turning hydrogen into helium, and in that process, it gives off a lot of energy as motion and as light. And that's where most of the energy from the sun comes from, and that energy makes its way out of the sun, and the sun then radiates heat out in all directions.
So before it starts creating helium, is there any light coming off of it, or energy?
Yeah. So light is caused by like moving charged particles. So any hot object that's moving, so like your body is giving off infrared heat right now and other spectrum of light. So any hot body, we call it black body radiation, gives off some characteristic spectrum of light from it. So like before you get fusion, that ball of gas will be radiating light out. But then with these fusion events, it's going to be radiating a lot more light, and it's going to get hotter in the core of the sun.
Okay. Yeah.
And you get this nice stable burning of hydrogen in the core of the sun. I'll just put some numbers to this. So our sun gives off about, so every second it's burning 4 million tons of matter into energy. So that's about 1 million elephants worth of mass per second. So there's not elephants in the core of the sun, but the mass equivalence of 1 million elephants is being burned every second.
That's fucking insane.
In the sun. And that's just dumping this energy, well, within the sun. It's like heating up portions of the sun itself, but then it's also giving off a ton of energy. So you might think like the sun's really massive, right? And massive things like to pull towards the center. but then the energy from fusion is pushing out the other way. So like you get this fusion in the sun, and that wants to get out from the core, but then you get gravity pulling back in. So you get what's called hydrostatic equilibrium, where the sun maintains a nice shape. It maintains a nice ball. It's not just going to contract inwards forever, because it's getting this outwards push from, we call it radiation pressure. So the light that's produced wants to get out, and the gravity wants to pull it in, so it forms a nice ball.
Wow.
And in that process, it's always creating helium from this hydrogen and burning and creating energy from the mass that was initially contained in the star. So in like this 10 minutes, I've just described, I guess, more or less what our star is doing. And that's basically what gives us all the energy that we get on Earth.
That's sick. Is the radiation pressure also being pulled in because of the electrons and protons attracting together, or is that different? Is it only... Sorry, you said it's radiation pressure going out or in?
Going outwards.
Sorry,
the gravity's pulling in. Yeah.
So is it just gravity pulling in, I should say, or is it also the positive and negative charges of the protons and electrons attracting it
Yeah,
together?
that will be a much weaker effect on average. So like the two main forces you kind of think about is gravity pulling in, and then radiation pressure pushing back out.
Right.
But yes, of course, there's these charged particles, and they are attracted to each other, but it's so hot that like it doesn't really matter too much. So the sun basically is stable as a plasma. And plasma just means like a soup of charged particles.
Right. Of protons and electrons.
Yeah. So, yeah, do you have a question you look like you want to ask?
Yeah. The role of the weak force again is to turn neutrons into protons and protons into neutrons?
Yep. Yeah, exactly.
So where does that factor into the radiation pressure again?
So that factors into the fusion process.
Right.
So you have a bunch of protons initially, and those are charged and don't want to be by each other.
Right.
So you get these protons clicking together for a brief moment, and then if the weak force engages and turns one proton into a neutron, that forms deuterium, which is just a proton and a neutron, and that's more stable than two protons stuck together.
Mm-hmm.
I'll just give the exact chain that happens in the sun. So you get this proton and neutron to form deuterium, and then you get another proton come in, and that forms helium-3. So you get two protons and a neutron, and helium-3, when that's formed, gives off a gamma ray, gives off light, which is energy. And then there's going to be a bunch of these helium-3s floating around, and those can smack into each other, and that's going to form beryllium-6, which is another element, but beryllium-6 is unstable. So that will decay into helium-4, which is really stable. So that's the helium that's being produced in the sun, and then two protons just fly off as a result, because those don't want to be anywhere near that. So eventually you get hydrogen turning into helium. The sun also doesn't just stop at helium. That helium can interact with other heliums and other protons, and eventually you can start to form heavier elements. So you can start to form like lithium, beryllium, boron, carbon, and stuff. So every sun has some amount of those other elements. And more or less in the lifetime of a star, it can start to create these progressively heavier elements like oxygen, all the way up to iron or nickel. But once you get to iron or nickel, which is, I believe, like 26 protons, so it's quite a big clump of this mass now, you can't get fusion events to happen anymore. because it's not energetically favorable for any more particles to stick to that. So you get this stopping point. So eventually in the core of a sun, once it's burned all of its hydrogen, it has helium. Once it burns all of its helium, it starts to burn more and more, and it gets like an iron core in the middle of the sun. And basically this is after billions of years that it eventually runs out of fuel, and that's what causes these supernova events.
So this iron core is a plasma form of iron, or it's what is the consistency of the iron core? Gas?
Yeah, so it'd kind of be like gaseous iron, which is like
whoa, sounds dense.
Yeah, but maybe it's dense enough that it forms a solid. I don't know the specifics on that. Yeah, but eventually it runs out of fuel to burn, and that's what causes like collapse of the star. And then if the star's big enough, it will undergo supernova, where it'll collapse in and then explode out. That exploding out actually is how we get all the elements heavier than iron, because that's such an energetic event that when the star collapses in, these elements don't want to be close together, so they'll rebound out in all directions.
So implode, explode with like so much energy. Like it's just absurd the amount of energy a supernova gives off. And that will produce, it's called the rapid process, or the R process. I think it's actually like rapid neutron capture. So there's a bunch of neutrons produced in that collapse, and then those neutrons can be captured by elements and form even New
bigger
elements.
So you get like gold, uranium, silver. So if you're wearing a gold chain or something, like that was produced at some point in like one of these supernova events.
That's fucking
of stars.
sick.
So basically anything heavier than iron. If you look at a periodic table, there's a crap ton of elements heavier than iron, and all of those had to be produced not just in this R process event, because there's another process called S process, which is like slow neutron capture, and that just happens kind of randomly during the life of a star, where slowly neutrons can be captured and produce heavier elements. But it's cool to just think that like a lot of the really heavy elements we see on Earth, like uranium, other things like that, were produced at some point in a supernova event.
Yeah, that's so cool. So, does every element on the periodic table have a gaseous state because of that? Because I would imagine in a supernova, they're all gaseous still, because it's high pressure, high temperature.
Yeah, so I think once it's hot enough, like anything will approximately have a gaseous state, but like it might not be a common state of it unless it's in these like very extreme conditions.
Right. Is plasma more quote unquote solid than gas? Or
I wouldn't
are there
say
certain elements that their hottest form is a plasma and they don't turn into a gas?
Yeah, so a gas is more or less understood as a collection of atoms that are not like bound together in any way.
Yeah.
Plasma is more or less a gas of charged particles, where it's too hot for the atoms to form. So it's just like a gas of these like atomic components.
So plasma sounds like it's hotter than gases if atoms can't form.
Exactly. Yeah.
Interesting. Okay.
Yeah.
I thought gas was the hottest.
No. Yeah. So if you've heard of like people talk about there being phases of matter, which are like solid, liquid, and gas, because that's what we encounter in our day-to-day life
on Earth.
But there's different phases of matter. There's plasma, which is in the sun, and then we can create plasmas on Earth. If you microwave a grape, I believe it
really
creates a plasma.
Holy fuck.
Because the skin of the grape like vibrates to the when you apply microwave radiation to it in your microwave, and then it creates little like plasma coming off of it.
That's fucking cool. Will that fuck up your microwave?
No, I don't think so. I think it's like just small enough, but
That's cool. Okay, so it's solid, liquid, gas, plasma.
Yeah. Then there's other more exotic states of matter, but
really.
so there's like it's getting a bit too much detail, but there's
What about erotic states of plasma?
So just another one if you want to look it up is Bose-Einstein condensates. That gets into a lot of like quantum mechanical stuff, which is just too much detail for right now. And then there's other weird states that scientists produce, but in stars, that's the relevant state is a plasma. Okay, so we got this star burning, I say with quotes, hydrogen, because it's a fusion process. And then that's giving off energy, so it's giving off light out into the solar system. And eventually, that light travels the 8 minutes it needs to travel to get to Earth. And that light is what basically gives Earth all of its energy.
Pause. How did planets form like Earth?
So our sun is called the third generation sun. We know that because we observe chemical abundances of like uranium, iron, gold, all this stuff on Earth. And for the amount of like these heavy elements to exist in the amounts that they do, there has to have been basically a first generation star had to explode nearby, and then other second generation stars also had to live and die and explode nearby. So you get enough heavy elements formed in those first and second generation events to then create enough heavy elements floating around.
What's the spectrum of lifespans of stars?
They can be, so if a star is really heavy, it actually doesn't last too long. It can die in like tens to hundreds of millions of years.
Wow.
Our sun's a pretty small to medium sized star. So our sun has lasted for, I think, about like 5-6 billion years so far. But it will last another, I think, 10 billion years before it dies. But our sun's not going to go supernova.
What?
Because it's not big enough. Our sun's like pretty average, small size. You need like big stars to go supernova.
Whoa.
Yeah.
So what happens to smaller stars then?
So they will collapse as well, but they won't have enough energy to like explode. So they'll kind of just like...
They'll implode only?
Yeah, they'll implode into what's called a white dwarf, which is, I believe, just like... what's a white dwarf exactly again?
Should we get the Googles going?
Yeah, we can look up what a white dwarf is exactly.
Because does that continue to burn? Do you know that? A white dwarf, it just at a dimmer...
Yeah, exactly.
light?
They'll burn. They'll be in like a stable arrangement for like
Another
100 billion years or something.
Whoa.
I'll consult.
That is not how I thought our solar system's future would be. I thought we were going to get supernovaed and fucking disintegrated, all of us.
No, so our sun isn't big enough to do that.
Wow.
Okay, so I just asked the ChatGPT. A white dwarf is a dense, Earth-sized remnant left after a star exhausts its nuclear fuel. It consists mainly of electron-degenerate matter, supported by electron degeneracy pressure, and gradually cools over billions of years. White dwarfs mark the final stage in the evolution of stars with masses similar to or lower than our sun.
Wow.
So electron degeneracy is kind of tricky to understand, but because it's like a quantum mechanical thing. Basically, electrons don't want to be in the same quantum state as one another. So I don't know if we've talked about this on the podcast, but you've learned about quantum numbers.
Yes.
And each particle can only have like a set of quantum numbers, and nearby another particle can't have the same like state. So like that exerts a pressure outwards. So it's not a radiation pressure anymore. It's like a degeneracy pressure. So these electrons don't want to... So gravity's pulling this white dwarf inwards, but then the electron degeneracy is pushing back outwards. That again, these are big words, but that just means the electrons don't want to be pushed in anymore. So it will just stay as sort of this hot ball of electrons about the size of the Earth. So that's what our sun's fate will be.
So that's what stabilizes the shape of a white dwarf, whereas the radiation pressure stabilizes the shape of a sun or a star.
Yeah, and if you have a star that's bigger than our star, you can get to what's called a neutron star, where instead of electrons being the final result of the star, it will have... So in the collapse event, it will have had enough mass and energy to collapse to the point of creating neutrons.
But still not enough to have a supernova.
So that the neutron stars, I believe, go through like a supernova as well, but it's just not as massive an event as like a bigger supernova, because massive supernovas create black holes at the middle.
Whoa.
So that's how black holes are formed. Is when
every supernova creates a black hole.
No. So I think it's the case that if there's not enough energy, it will just create a neutron star after its supernova. But if it is big enough and has enough energy, it will create a black hole at the middle. So I think if you have a supernova, you can end up with like a neutron star or a black hole at the middle.
Okay.
So neutron stars are like white dwarfs, except it's not electron degeneracy, it's neutron degeneracy, where these neutrons don't want to be any closer to one another, but they're as close as they can get. So neutron stars are kind of cool too, because a teaspoon worth of a neutron star will be heavier than like mountains on Earth.
Wow.
Yes.
Wow.
So when they say there's like so much empty space between atoms and stuff, you can picture that as like the mountain that I'm looking at has a crap ton of rock, but there's a lot of empty space, so it's like kind of a big structure.
Right.
But neutron degenerate stars
have zero empty space.
Have basically no empty space between them. It's just like as dense as you can get of neutrons.
Damn.
So like a teaspoon worth of that will have as much mass as like a mountain. I think that's like the relevant scales here.
That's insane.
So
okay. Smaller stars implode into white dwarfs.
Yeah.
Medium, I guess, or a little bit.
Yeah, definitely larger, much larger than our sun. But
okay,
yeah,
larger-ish stars break down into a neutron star.
Yeah.
Big stars, supernova, and if they're not big enough, they'll turn into a neutron star. They'll come back down into that.
Yeah.
Which is going to burn forevermore, or will it?
Yeah, that'll just kind of be like stable like that.
Stable forever.
For a long time, like they'll
like more than 100 billion years.
Something like that. Like it's a long time.
Okay. Do you know what they eventually would turn into?
I think. Let me consult the.
And then just to finish up my summary, and then a large supernova though turns into a black hole.
Yeah, let me read off here. So a neutron star is a highly compact celestial object formed from the remnants of a massive star that has undergone a supernova explosion. It is incredibly dense with a mass greater than that of the sun, but compressed into a sphere only about 10 kilometers in diameter.
What?
Neutron stars are composed mostly of neutrons and possess intense gravitational fields, making them unique and challenging to study.
They're tiny, man.
Yeah, they're tiny.
10K in diameter.
Yeah.
But the heaviest motherfucker.
Yeah. Okay, sorry, I was just reading about there's other exotic bodies out in the universe and galaxies.
Is there time to talk more about this? I'm
fascinated. Yeah. So there's quasars. So quasars, scientists kind of discovered them, I think by accident before they had the theories.
Sounds like an exotic brown man name.
Quasar?
Yeah. Go on though.
So quasar is short for quasi-stellar radio source. So the reason that's the case is that we were observing the sky with like radio telescopes, and we would see like a signal that was very repeatable. It was very repeated in time. So you'd get like signal, and then it would go away, and you get signal, go away. So that signal was like very periodic and happening like at a very fixed interval. So they're like, what the hell are these radio sources that are so stable? And what that is something. So it's this quasar. So a quasar here is a supermassive black hole, and they emit intense radiation across various wavelengths, including visible and radio waves. So they're rotating and basically giving off like beam of radiation.
Do most black holes not rotate?
No, most would as well. And black
okay.
holes can get quite exotic in like their behaviors as well.
So like there's different types of black holes, like many different ones. Quasar being one of them.
I think most black holes will behave in similar ways. So they'll be like rotating and have like this quasar characteristic.
Most do have a quasar characteristic.
Okay.
They emit these radioactive waves.
I don't know for sure.
Okay.
I'm out of my.
Sorry, go on though about your quasar description.
Yeah, so basically you're getting these rotating radio wave sources that are these black holes that are emitting light, and that's what gives this periodic signal that these astronomers were observing. But yeah, let me look up. There's another thing called a magnetar. Let me see what that. Okay, so the magnetar is what I was thinking of. So it's a type of neutron star with an extraordinarily strong magnetic field, thousands to billions of times more powerful than typical neutron stars. These intense magnetic fields can lead to dramatic and sporadic bursts of X-rays and gamma rays. Magnetars are thought to form from the remnants of massive stars that have undergone supernova explosions. The extreme magnetic fields make magnetars fascinating objects for astrophysical study. So that's what I was thinking. So a quasar would be like this rotating black hole that's giving off energy, and then a magnetar would be a rotating neutron star that has these strong magnetic fields and give off these bursts of like X-rays and gamma rays and stuff.
So those would be an entirely different force than what the radioactive waves coming off a quasar is?
Yeah. Sorry, I'm just reading more about magnetars here. Magnetars also exhibit unusual characteristics such as rapid rotation and occasional glitches in their spin rates. Cool. Okay, yeah, so that's more or less what I wanted to talk about with these things, but if you have more questions, we can look into it more.
By the way, Jordan's saying ChatGPT for questions like this is way better than Google. That's a valuable note for me.
To first order. So like what I mean is that if you just want to know quickly, you can ask ChatGPT, but it's like limited in unless you like can probe it enough to get the information out. But if you want to know way more detail, like the Wikipedia will have like other things, or
I think most people just want the summary.
Yeah, so if you just want a summary, ChatGPT would be good to just ask
for
it
the
this
win.
stuff.
Okay.
Yeah. So let's get back to tiny baby stars like our sun.
Okay. I think we left off before we went on this tangent about how planets are created. Because did you answer that?
No. So I was saying that our sun is a third generation sun.
Yes.
So when our sun was formed, there was a bunch of heavy elements as well. So you get like these clumps of matter. So like after a supernova, like there's matter all over the place, but there's still gravity. So eventually mass will then start to recoagulate. So all these heavy elements produced by the supernova can then recoagulate into another like stellar nursery where new stars are born. And in that neighborhood of like our sun, for instance, there's these massive elements that will also coagulate into like hot, like rocky bodies
Because of gravity.
And that's what's like forming a solar system. So our sun was formed by like this recoagulation of like hydrogen and other elements into forming our sun. But then like nearby it, there was also this coagulation under gravity of like rocky material, which formed like our Earth or the asteroids or the more distant planets, which are big gaseous planets made of other elements.
So it all depends on the concentration of gravity, like the pockets of gravity within space-time, right?
Yeah, exactly. So Jupiter, actually, people call that a failed sun because it wasn't
Wow.
massive enough to create a sun.
Would that have been a binary star system for how
Yeah,
close it is
so
to our sun?
that's exactly where you get binary
Whoa.
star systems, is that you get these like stars forming nearby, and then those stars will be rotating each other.
Sick.
But Jupiter wasn't large enough to create that type of system. But yeah, that's another cool point, is binary star systems are all over the place in our galaxy and in the universe, where you get
They
these-
rotate around each other.
Yeah, they rotate around each other, and then you get more complexity of like planetary orbits and stuff. Like our orbit is quite stable and nice around our sun, but if you have binary stars, it's a bit
I feel like it would make it hard for life forms to exist in a binary star system.
Yeah, I think it's definitely possible, and I think
It's possible still.
astrophysicists are looking into like I think there's candidate planets that are around binary stars still
That could harness life in
Yeah.
the conditions that we're familiar with.
Yeah, I think it's just a bit trickier, as you say,
It
but
seems like it. If two suns are rotating around each other,
yeah,
that's very different temperature fluctuations, in my opinion.
yeah.
So not stable enough for
It-
life to form, I would think.
Yeah, I think maybe life as we know it would be not quite the same, but
Yeah, I think obviously any other planet that could have life in the whole universe, it's going to be a different life than we're used to. I think like the
Yeah.
planets that they say are similar to Earth, sure, like they can
like we look.
it could be a host for similar life forms to us, but there could be totally different life forms that could
Yeah, like
come up
we
in
know
completely
of how,
different environments.
we know of how life can be formed if you have enough like carbon and water, liquid water. Like, so when we look for candidate planets that might have life, they typically look for planets in what's called the Goldilocks zone, which is where the planet's in a comfortable temperature where liquid water can exist. Like it's not too cold or not too hot type thing.
Right.
Because liquid water seems to be really important for our type of life. But
Yeah.
like maybe there's different types of life, like
Totally.
because our life is carbon based, because carbon's really versatile in the types of bonds it can make. But like for instance, silicon
Is also very versatile.
is also versatile, but it would just be like a more exotic life form type state. But like we do know the chemistry that our universe seems to exhibit, which if you look at a periodic table, like that's the chemistry. Like those atoms on that periodic table will be the same atoms in the Andromeda galaxy. So like we can think that we're quite constrained and look for life forms similar to ours, but like you say, like there's potentially more exotic or different pathways for life to manifest.
Right. That's cool. So, yeah, higher pockets of concentrated gravity can either pull in elements to form a planet or a star.
Mm-hmm.
And then going back to what you're saying about the sun's light taking 8 minutes to get here
Mm-hmm.
to Earth, and I think that's the spot you left off.
Yeah. So like once you get these planets formed and whatnot, like our planet thankfully was formed in this perfect distance from the sun that it's not too hot and not too cold. So like the light from the sun gets to the earth, and that's heating up the earth. But then the earth will also give off energy, and like if the sun gives us more energy, our earth also gives off more energy, so it really reaches an equilibrium. And you can calculate with like thermodynamics what temperature our earth should be. If like, so you'd basically just calculate the sun has some intensity of light hitting the earth, and there's equations that dictate like intensity of radiation to temperature. So you can calculate what temperature our earth should be, and it comes out to being like minus 15 degrees Celsius or minus 10 or something, which is not what we observe. So we're like, okay, why is this math different than what we would observe? And it's like, oh, okay, our earth has an atmosphere which retains some of that heat and keeps our planet warm. So what we actually observe on Earth are like temperature ranges from like minus 40 to plus 40 Celsius.
Ish, yeah.
Ish, depending on like where you are on the planet. So planets that are at the equator get the most sunlight and will on average be hotter than like the poles, which get much less sunlight. But then you also have the Earth tilted. So depending on what season it is, which just means at which point in the Earth's orbit around the sun you are, at some point, so for our summer, the North Hemisphere summer, which is from like, what, June to September, at that point, so from June to September, the North Pole is tilted towards the sun, and that's why the sun doesn't set on the North Pole. So if you go on a trip to like Greenland or Iceland, during the summer, the sun won't really set, depending on the latitude that you're at. But if you go in the winter, the sun will never rise because we're now on the opposite side of the sun, and the North Pole is tilted away from the sun. So that's what causes the seasons on Earth. So when we're in winter, our North Pole is tilted away from the sun, but the South Pole is now tilted towards the sun. So that's why like Australia has summer during our winter.
Yeah.
So then the sun wouldn't set on Antarctica during their summer type thing.
Yeah.
So you get these like differences in the amount of light the Earth is getting at different points in the year. And that's what causes the seasons, but it also causes weather patterns. So for instance, if a region of the Earth is getting heated, but another region is not getting heated, you get this gradient of temperatures and pressures. And when you get these gradients of pressures, that causes wind to flow. So then you get the weather patterns that we see on Earth.
Because one section of the planet is receiving
Yeah.
sunlight and the other isn't.
So when you watch the Weather Channel, they'll put like the H and the C on the map for like hot and cold, and these are like different air pockets that are higher pressure, or I think they put H and L for like high pressure, low pressure. So then you get like the low pressure systems moving towards the high pressure because it wants to like fill in that space. So low pressure air is more dense than high pressure air. So that density wants to flow into the lower density portion, and you get these like wind patterns that we see on Earth. So then you can start to build weather models and like predict like weather patterns and rain patterns, and like that's basically what meteorologists are doing, is getting data from different points on the Earth and then using that to inform their weather models for like where the wind and rain and temperature is going to be like flowing across the planet. And all of this comes from the sun. Like you can trace most energy sources on Earth back to the sun at some point. So like wind originates, the wind itself doesn't originate in the sun, but like
it's caused by a process that originates from the sun.
Yeah, exactly.
Wow. I thought it was the moon for wind.
No,
tides and shit.
Tides are affected by the moon, but also by the sun. We can get into tides as well, but here, let me just wrap up what I wanted to talk about here. So the sun's light hits the Earth, And that heats up the atmosphere, so that gives like energy of like the temperature of the earth. But then it also gives more familiar energy sources we're used to. So solar power, if you set up a solar array, you can collect that sun's energy directly. So that's one power source that we can get on Earth. Another is when a plant undergoes photosynthesis, there's basically carbon dioxide in the air near the plant. And then if light interacts with that carbon dioxide, it can kick off the carbon and the oxygen. So it can split that C and the O2. And then that C gets collected by the plant. So the plant's collecting carbon, and as a byproduct, it's spitting off oxygen. So that's the oxygen we breathe, which is kind of nice, but it's just a waste product of photosynthesis. So the sun collects this carbon, stores it in its wood, and then we can chop down the wood, burn the carbon with combustion that I described in the other episode, and we can harness the energy which came from the sun, came from the light.
Sorry, I think you said the sun collects carbon at some point. You mean the tree collects carbon? And,
yeah, sorry,
and
did I
wood?
say sun?
I'm pretty sure, yeah.
Oh, yeah, the trees collecting
Sorry,
the
I
carbon.
was just hung up on that for a sec.
Oh, my bad.
Okay, yeah.
Yeah, so the tree is collecting carbon
Yes.
from this photosynthesis process, but
Yeah.
that
Keeps
process,
it in the wood.
Yeah, it keeps it in the wood, and then
Oxygen comes off.
oxygen comes off, but then we can burn that carbon later and use that energy, which is
Nice.
essentially like stored sun energy. So again,
crazy.
that energy mostly came from the sun. If we don't harness that wood's energy, like that wood, like the tree will fall down, it'll decay, maybe it gets buried under the soil for like millions of years, and eventually, I don't know the exact process that creates oil and gas, but that's what oil and gas is. It's like dead organic matter that then we can drill up and burn later in combustion again and use that to fuel our cars. But that's more or less, if you follow the chain back in time, that energy came from the sun.
Wow. So, speaking of oil and gas, I thought that was like mostly dinosaurs that...
No,
Is that bullshit?
that's bullshit. Yeah.
It's all organic matter.
Well, dinosaurs are organic matter, so like, sure, if you
So
had
partially,
yeah, if
but
like
a small fraction, I would
yeah,
imagine.
I don't. It's like impossible to quantify that as well, but it's more so just like dead organic, like probably like leafy type, or it
Wow.
could be like small other life forms or something, but just like if they're collected and decompose or whatever over time and coagulate into this oily substance that we then can use later as fuel.
Hmm. So when they say fossil fuels, that can be any range of fossils, not just fucking dinosaurs.
Yeah,
Because,
so fossil fuels, like
fossils can be wood, like petrified wood and shit.
yeah,
and
so
all
like
that.
the fossil of organic compounds, but like fossil fuel is a bit of a misnomer.
Right.
Okay. But yeah, just to like wrap it up. So yeah, most of the energy we make use of originated in the sun in those fusion events. And like, to me, that's cool because it's like, no wonder why like people praise the sun as their god.
Mm.
Like those people are the wise ones. To,
Like Queens of the Stone Age?
yeah, our god is the sun, exactly. So like that if you're gonna praise something as your god, I think praising the sun is a good bet because that's like what gives us all of our energy.
Right. It's
On
constantly
Earth.
providing.
Exactly, it's the giver of life and energy.
Dude, I didn't connect those dots with like the carbon in wood, for example, being from the sun.
Well, the carbon is just carbon that's around in the atmosphere. Like the carbon doesn't fly from the sun.
Okay.
Here, but the light from the sun hits the carbon dioxide in the air, and then that, in combination with the molecules in the plant, do this photosynthesis process. But like, it's the light from the sun that gives that initial energy for photosynthesis to happen.
Oh, okay.
Yeah, but the carbon it was just in the
atmosphere.
air. Yeah.
And it's cool how the waste products of a plant give us oxygen, and our waste products of our breath give plants
Carbon dioxide.
Carbon
So it's this
dioxide, yeah.
nice little cycle,
Yeah.
which, I mean, it's not perfectly self-sustaining, that cycle, but there's other sources that we have enough carbon dioxide and enough oxygen for us to do our thing and live a life. And
Have you heard the stat that 85% of our oxygen actually comes from algae?
yeah, that makes sense, I think.
It's crazy.
Yeah.
It's a lot.
Yeah.
Only 15% comes from plants.
Okay, I was thinking of lichen. Algae is I think just like a plant matter, but then lichen is
oceans.
like the lichen is a combination of like this plant matter with fungus. So like fungus and algae like learned how to live off one another in a mutually beneficial way.
Cool.
So then like lichens are basically like plant funguses that have like this mutual codependence on one another.
Wow.
I was when you brought up algae, I was thinking, is algae the fungus thing? And it's like, no, that's just algae is just the plant matter.
Right. And just to make everyone worried about fucking the world, or not fucking the world, but our world, all the algae in the world depends on the ecosystem of oceans
Mhm.
continuing to exist in the way that they do.
Right.
And as we overfish, it's eliminating entire species from the ocean systems. So the less fish there are in the oceans, the less algae there is, meaning the less oxygen there will be on Earth. And that's a big problem.
Yeah, like everything is connected on many levels, and for us to think that we're like this isolated, independent system from the Earth is just absurd.
Yeah, it's ridiculous. So there is a documentary on Netflix called Seaspiracy, and it talks all about this, where if we continue fishing at the rate that we are, we're going to have to put serious bans on our planet's fishing within the next, let's say, 30 years, because in 50 years, if this continues, they said there will be like less than half the oxygen there is now on Earth.
Is that right?
Yes. Like
Okay. Well,
and
I'll
this
have to watch
is
it.
in my opinion one of the biggest issues that no one's talking about, but yeah, it's interesting if you guys want to check it out.
Okay. I'll
But
check it out.
I could see us continuing at this rate because the fishing industry is so big and people don't want to do that until it's like almost too late and like oxygen is like in
Yeah.
high risk territory, and then all of a sudden fishing is just like banned or something.
Yeah.
That's how humans tend to fucking operate. Reactive as fucking, not proactive.
I hope that we can survive thousands or millions of years, but man, it's like giving a toddler a fucking Glock. It's like bad things will happen before good things happen.
So true. It's ridiculous.
Okay. Holy crap, it's been an hour.
Let's go.
Okay. I have another cool thing that's not quite related to suns and stuff, but it's a similarly like cosmic event that is just cool to think about. So here's the sensationalist summary, and then I'll get into what's actually happening. So every second, around 30 tiny little bullets are traveling through your body near the speed of light and are basically like destroying like molecules along its path through your body.
What are these bullets?
So that was the sensationalist headline. So these bullets are the electron's bigger brother called muons. So when you look at like a table of the fundamental particles, there's not many. There's maybe like 20 fundamental particles that exist. And the electron has two bigger brothers. One's the muon and one's the tauon. So they're basically like the electron, just a bit chunkier with more mass.
Chunkier than an electron?
Yeah, so
But not chunkier than a neutron.
No, so neutrons are from a different family of fundamental
sorry.
particles.
Okay.
So neutrons are from like built up of quarks, which are like another basic thing.
Okay.
But this electron family is called like the lepton family.
Right.
So if they had a last name, it would be the leptons would be this family. And there's 3 little brothers in there. There's electron, muon, and tauon. So muons are unstable. They don't last for very long. They'll decay into an electron. So it's like the muon had an identity crisis and is like, the electron's the favorite child. I don't want to be a muon anymore. So it'll like undergo some transformation down into an electron. So then you might ask, like, how do these muons come about if they're unstable? So the picture to think of is like the Earth's atmosphere. And if in the Earth's atmosphere, there's all this gas kind of just chilling like around the Earth. And what happens?
You wonder why I keep looking behind you is because there's a picture of the Earth, and every time you talk about it, I look at it.
Yeah,
like,
perfect. So you
okay.
can visualize there.
Yeah.
So what happens is in our galaxy, there's all this like matter kind of flying around because a galaxy is a pretty energetic thing. Like that's just like the galaxy is just the collection of stars in our Milky Way galaxy. And there's basically protons and other particles kind of just flying around. There's also strong magnetic fields in our galaxies, which can accelerate these particles up to like speeds near the speed of light. So in our at the top of our atmosphere, there's this bombardment with like protons and other cosmic particles that smash into the upper atmosphere and create these showers of particles that then like kind of rain down, you could think of, onto the Earth.
And muons are some of them?
And muons are some of them. So
neutrinos are others?
Yeah, so there'll be like neutrinos, muons, pions, like all sorts of exotic. So it's like having a particle accelerator, like a CERN type particle accelerator, like up in the atmosphere.
Dang.
So muons are some of these, and these muons are flying from upper atmosphere and down onto the Earth, like kind of showering us with these near speed of light particles.
Are we only vulnerable to them when we're outside?
No.
So they travel through the fucking roof.
Yeah, so they get,
wow.
Let's say we have concrete above us. Like they will get what's called attenuated by concrete. Like they'll get blocked by each layer of concrete, but some will still go through our bodies.
What if it's wood?
Yeah, if it's wood, it's just less so than concrete. So like if we put a sheet of lead above us, we'd probably be clear
Protected.
of muons. That's why they build some certain physics setups like deep underground, because you don't want muons to interact with your setup.
Wow.
And there's other cosmic particles like gamma rays that you don't want to interact with your experiment.
So they disintegrate us, you're saying?
Yeah, so I was getting a bit carried away just to like get your attention with it. So so these little bullets, I call them bullets, but they're tiny, tiny, tiny fundamental particles, like on the size of an electron, which is really, really tiny. But they're charged, and when they fly through our body, the charge of them and their speed is basically a lot of energy that can basically rip like bonds of molecules and atoms apart as it passes through your body. That's called ionizing radiation. So when you get an X-ray scan, X-rays are also ionizing. So X-rays are also ripping electrons away from their orbit in atoms. So that's called ionization. So anytime someone talks about radiation being a bad thing, that's why it's bad, because radiation, more specifically called ionizing radiation, rips away electrons from orbits in your body, and if it happens to be electrons that are at the DNA strands, it basically rips your DNA apart, and then your DNA has to self-repair, and it can repair to incredible accuracy. So like your DNA can repair very reliably. Like it's like 999,000 times out of a million your DNA will repair itself properly, but that 1 out of a million times it might misrepair. It's actually probably way more robust than that. So it might be like 1 out of a billion times it might misrepair, or even more.
So, sorry, just a quick pause because it hasn't left my brain since you brought this up. Microwave radiation. If I'm putting my food in the microwave a million times or a billion times, will my DNA potentially not repair on number 1 billion when I eat my fucking microwave food?
So microwaves aren't ionizing.
But it's still radiation, right?
Yeah, so that's where I put the word before radiation called ionizing radiation.
Okay.
You need to specify so our sun is giving off radiation, but that's visible light, that's infrared light, that's microwave light, that's radio wave light. Like these are all low energy lights, and those are not ionizing. Those are all not ionizing.
Nice.
Our sun is giving off some amount of X-rays and gamma rays, which are ionizing, but that's just like we call it like a background dose of radiation, of ionizing radiation.
Right.
There's also gamma rays flying in from the galaxy. So if you think of the spectrum of light, like where visible is like in the middle, to like lower energy light, you go from visible light to infrared to like microwave to radio wave. Those are all low energy lights. Then if you go the other direction, you get into like ultraviolet light or UV, X-rays and gamma rays. So gamma rays are the most energetic light, but it's all still light. But gamma rays are also flying in from the galaxy, and those are also hitting our bodies and ionizing molecules and atoms in our bodies. So gamma rays can break DNA. These muons can break DNA. When you go to your dentist and get an X-ray scan on your mouth, that can also break DNA. And what I'm getting with this of breaking DNA is that if DNA misrepairs and basically glitches, then that's what cancer is. It's like this growing, misrepairing, like malfunctioning cell.
Holy fuck.
So it's basically like this, like most cells have like clear death processes, but when a cell is malfunctioning, it somewhat like forgets how to die, so it just starts to grow, and you get these like cancerous clumps.
Should I be fucking declining the X-rays at the dentist from now on?
No, yeah. So you don't decline it, because it's like
because they're looking for other shit too.
The amount of radiation you get from that X-ray,
it's fuck all.
It's not fuck all. Like it's it contributes to your like yearly dose. Like we usually track the dose we get. So dose, I'll just define it as like the amount of ionization events that have happened in your body. So if you have a high dose, then that's not good, because high dose correlates with like high cancer probability. So the higher a dose you get, the more likely it is for cancer to develop. But like the amount you get from like a tooth scan or whatever is like not going to significantly increase your cancer probability too much. So like we don't consider it safe, because you wouldn't just go in and get a tooth scan every single day, because that's just dumb. But if you get like a couple a year, like that's not really gonna decrease your survival probability over the course of your life. Like if you don't get that tooth scan and like your teeth start to fall out, that's gonna kill you more likely than getting that X-ray. So it's like you shouldn't just stop doing these things.
Yeah.
And again, we're always being bombarded by these muons. We're always being bombarded by gamma rays
coming in from space.
You're not just gonna box yourself in a lead room your whole life type thing. So it's
what's the highest exposure to them that we get in life? Is it just existing?
Yeah,
and
so
the shit coming in from space, or is it like X-rays, or is it
so
nuclear energy?
Yeah, that's a really good question, because depending on where you are on the planet, the soil has different amounts of like radioactive material.
Wow.
And if you've heard of radon gas, that's a really bad one, because if you have a lot of radon gas, like particularly if there's like some buildup of radon gas in your house for whatever reason, radon gas is radioactive. So if you breathe it in, it goes into your lungs, and then the radon decays by what's called alpha decay. So it shoots off a high energy helium nucleus, which is called an alpha particle. And those alpha particles can ionize cells in your lungs. And that is a dose of radiation. So people that are breathing in radon gas will get much more. It's still considered a natural source of radiation. So I'll just list like the natural sources. So radon gas is one, and that's the biggest natural source for a lot of people. Another source are these muons and gamma rays coming from like outer space. We call those cosmic particles. Another is just like common elements or isotopes of elements that are radioactive. So potassium, in every banana, most of the potassium is a stable isotope of potassium, but there's some amount of radioactive potassium in any amount of normal potassium you eat. There's just like common ratios of like stable potassium to radioactive potassium. So in every banana, there's some amount of radiation in the banana or in anything you eat that has potassium in it. Mm-hmm. So like eating potassium, or just the amount of potassium that exists in our bodies, is a dose of radiation. Sleeping beside your partner at night is also a dose of radiation, because they have potassium in their body, and other radioactive compounds also in their body, and that's going to dose you as well. Whoa. So you're getting natural doses from a lot of sources. Also in soil, there can be like some amount of uranium or other radioactive elements in just like daily soils you interact with, and those also can give you radiation. So like you're getting radiation all the time throughout your daily life. And in theory and in practice, those do and would cause cancer, but it would just be like an unlucky type thing because it's still a fairly small dose. But for instance, pilots are flying in the upper atmosphere, not quite where these events are, because these events are happening much higher, but there's more muons flying through them when they're doing their flight. So pilots have a higher yearly dose of radiation than people down on the surface would have. So like I think they have to limit their flight time because of like radiation dose.
Holy.
I think the more immediate limit of flight time is like just stress and exhaustion, because that's unsafe for operating a plane. But I think they do still have to monitor like radiation to some extent.
Yeah.
And then definitely like astronauts have to monitor their radiation as well, because there's not an atmosphere to protect them from high energy ionizing events.
Wow, this is cool to know.
Yeah, so speaking of like muons, that's what my undergrad thesis was on, was like building detectors for these.
I thought it was neutrinos.
No, is muon detectors. So basically, like what the detector would do is you'd have this like plastic block that when muons would fly through it, it would leave like a trail of ionized plastic molecules in the block, and those molecules give off blue light, which then you put a little light detector inside a box with this plastic, and that light will pick up the light detector will pick up the blue light, and then you can count that as an event, as a muon event. So you can start to count muons, and the rate of those muons coming in, like I said, there's 30 going through your body every second. the rate of muons is about 1 muon per centimeter squared per second. So if your body is like this 30 centimeter squared block facing up into the atmosphere, then you're going to get 30 muons per second going through your body.
God bless.
Thank you. So yeah, I mentioned the potassium. So with the amount of potassium in our bodies, there's about 4,000 decay events of that potassium in our body every second. So every second your body, all the potassium in your body, there's about 4,000 decays into these, they're called beta minus decays, where the potassium will decay into another element and shoot off an electron. And that electron's what's ionizing matter in your body. So every second, about 4,000 of those events are happening in your body all the time, plus the 30 muons coming through from space. Yeah, so this is going on all the time. Okay, that's where I'm done with those explanations.
Nice. That was a lot of stuff. That's good. So yeah, being that this is a general science episode and you're all done with what you had prepared, are you ready for questions now?
Yes.
Oh yeah. Okay, so I have 10 questions prepared for Jordan. I know this is already getting to be a long episode, so I don't know if we'll get to all of them, but the first one, I was wondering, because every time I shower, I get out of the shower and I come into my living room at some point and I notice all of my windows are fogged up, and I don't know, the bathroom's a decent distance away from my living room windows. So my question for you, sir, is why is the steam traveling this far, and how is it traveling this far?
Yeah, so I mean, your room is like a contained system. The air out here is cooler than the air in your hot shower room. So your shower's producing like water, but then it's also hot, so then some of that's coming off as steam and kind of just floating out into the bathroom. Then if your door's open, you're letting in low pressure cool air into the bathroom.
Right, it's similar to the weather.
It's like a wind type weather event. So now you get gradients of pressure, and the air, like this room naturally wants to be at like an equilibrium pressure. It wants to be the same pressure everywhere.
The same temperature. Temperature is pressure, right?
Not quite.
Okay.
So pressure is like the amount and roughly the energy of those particles in some space. So like in the bathroom, there's like hotter air, but then out here there's cooler air, and it's like more dense than hot air. So that density wants to balance out.
Right.
So like more particles want to float to where there's less particles. So if you do that, given enough time, the particles from the steam from your bathroom will make its way out here.
So are they bouncing off walls to do that? Because it's not a straight line,
yeah, I mean,
really.
It'll kind of just flow.
It just disperses.
It'll flow its way
different
through
directions.
here. It'll follow like the general like concentration gradient, and each individual steam particle or each individual water molecule will have a different path to the window, and not all of them will get to the window. Like some will be in your kitchen, some will go to your room and stuff, but like the ones that do get to your window then encounter this cold glass surface, and that cooling is like when that hot moist gas cools down on that surface. Now it can't exist as a gas anymore because it's cold. And that's what condensation is like this liquid collection process on a surface. So it's a cold surface which is cooling this hot gas. So it's like kind of like reverse evaporation, where evaporation is coming off of a surface into the air as gas. Condensation is going the other way, where it's coming from the gas onto like the surface. Does that make sense?
Yeah.
Yeah.
Cool.
So yeah, it's again, it's like you think you're isolated in your bathroom over there, but everything's really connected in ways that you might not find intuitive. But
So steam travels in all directions out of the bathroom, and it's attracted to the concentration gradients or wherever there's a low concentration around there, and it'll fill that in with the steam.
more or less, yeah.
And then eventually end up on the window in a condensation process.
Yeah. Like the steam that makes its way there will kind of have no options aside from condensing on that material or on that surface, which is your window.
So the steam will go from the window to the wall, and some sweat will drop down my ball.
Yeah, as a
Down skeet,
as a wise philosopher once said.
Okay, cool. Thank you for that. Okay, next question. Briefly explain DNA, RNA, cells, and the function of as many biological organisms.
Orgasms.
Biological orgasms.
See, when
Function.
when a man loves a woman.
Explain as many biological organisms functions as you know.
Okay. Man, biology is so cool. Like the more you learn about it and not the way they teach you it in school.
Well, the shit you were showing me yesterday with the strands of DNA and the rule sets essentially that they all follow.
Yeah, it's basically
mind-blowing.
like nature has learned how to code in a way more cool way of coding than humans could ever have
It's
dreamed
sophisticated.
of. It's super sophisticated and awesome. We should do a full episode on this. I'll kind of give like broad overview. Okay, so we talked about bits in the what's it called? Alien Information Theory episode.
Episode 2.
Where you can take on one of two states, which is 0 or 1. Your DNA is basically has learned to code in a 4-bit or 4-state system. So your DNA uses 4 different letters as its coding language. So it uses A, T, C, and G. Each of those are just different proteins, basically, different building blocks that if you go along the strand of DNA, you'll get like a sequence of these letters in some combinations. So you'll get like A, C, G, T, 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 A, C, and like for hundreds of thousands or millions of those in a line. And that's every person has a different like DNA sequence, and that's what makes you who you are, is what DNA sequence was decided upon your conception. So yeah, your DNA is like chilling in the nucleus of your cells, and the book we were reading yesterday calls it like the throne room. So it's like it's the king just chilling in the throne room of the cell. And what happens is certain proteins, or we call them enzymes because they're like doing work, is these enzymes go to points on your DNA and start a transcription process.
So proteins in action are enzymes?
Yeah.
Okay. Go on.
So when you want your DNA to do a function, you don't want to take the DNA itself out of the throne room and like disturb the king too much. So like you're just going to go up to the king and kind of ask him what he wants you to do, and you're going to write that down on like a notepad, word for word or letter for letter. So this is the transcription process. where a enzyme goes up to the DNA, latches on to some letter, and what it has to do, so your DNA is like two strands bound together in this double helix. So it has to peel these strands apart in order to start reading off the digits or the letters from the DNA.
What are these actual letters like?
The AC,
yeah,
T,
but
and G.
the
names.
They're not actually letters. Like, what are they representing?
Oh, they're like they're collections of molecules into like certain proteins that are existing.
Right. So it's the enzyme is binding to certain molecules.
Yeah.
That's what's going on.
Yeah.
But yeah. Continue with letters. Like
yeah,
letters,
like letters.
molecules.
Yeah.
The letters stand for a molecule, right?
Yeah, exactly. Yeah. There's like a very there's a chemical structure that you can draw on a piece of paper, and chemists know the exact like what's in those molecules. But for our purpose and most geneticists' purpose, you just call them ATCG. Because you don't have to
They're
worry.
abbreviations, essentially.
Yeah, it's just like a stand-in for what this common structure is.
Okay.
So what the enzyme's doing is it latches on to the strand, pulls these two strands apart of the DNA, and starts to read off these letters, and starts to make a copy of it. And it's making a copy on the messenger RNA. So let's go back to the analogy. I'm this enzyme. I walk into the throne room. The king wants some functions to happen.
Who is the king?
The DNA.
Okay.
So I go up to the DNA. I start reading off all his instructions. So I'm like writing these down on my piece of paper, which is the messenger RNA. And then once I've got the message, so actually acquiring that message is quite complex. Like reading off certain chunks of the DNA, that's this like very complex thing. Like which instructions am I taking from the DNA at any given time is dictated on many other factors. But more or less, I'm getting some instruction packet from the DNA or from the king, writing it down, and then taking it out of the throne room, out into the cell. And then I have a bunch of workers and building blocks that these workers can use in the cell. So I go out into the cell and I find a ribosome, which can just be like, let's say you're the ribosome, you're like this builder, and I basically feed in letter by letter my message to you, and according to what's on that message, it turns out to be every 3 letters of my message correspond to a protein or to a amino acid or to it's basically one type of building block. So you have about 20 building blocks at your disposal that are just hanging around, and according to
are all the amino acids or amino acids and other things?
No, so it's the amino acids that are coded for by these 3-letter chunks of this message. Right. So you read the message I give you 3 letters at a time.
That tells me which amino acid.
Yeah, let's say the 3 letters are ACC. That corresponds to an amino acid. So you basically like start with that, and then you read the next 3 letters, and you're like, okay, that's a different amino acid. I have that over here. Chunk, you place that on top, and you start to stack up all these amino acids. Building. So you're basically building from my instruction some chunk or set of amino acids. And then what happens is that once my message is done, you stop building, and then that structure you've built basically doesn't just want to be like a stack of blocks, so it like branches out into 3-dimensional space according to some rules. And what that has now done is given us a new protein. So the message I got from the DNA is, what protein am I going to build when I go out into the cell? And then
so use proteins building more proteins through this process.
Yeah, so it's the DNA basically telling the cell what proteins it wants to build. And then those proteins can then influence the cellular environment and can change what's going on in the cell and can do different functions and do basically useful things for life.
That's sick. Can I briefly give a summary of what
Yep.
you've just said so far? So, a protein in action, being an enzyme, enters the DNA strand with an mRNA accompanying it.
Yeah.
It gets the code from the DNA written down essentially on the mRNA, and then it takes that mRNA, delivers it to a ribosome builder,
Mm-hmm.
and the builder uses each sequence of 3 letters or molecules that these letters represent and builds a new protein, and that new protein, based on the chemical structure, creates something new within 3D space?
No, so that protein itself is, so like
Is 3D?
is 3D, and
Okay.
it folds out into 3D space, and according to that structure, it will then have various functions that it can do.
So the ribosome makes it 3D.
Yeah,
It builds
exactly.
it into
builds it,
something.
and then it just folds itself out into 3D space.
Wow.
According to like certain rules that they've now figured out with AI. So if you look up like AlphaFold, they've learned how to map from that mRNA
2D
structure
code.
to the 3D structure of the protein.
Sick. Okay.
And then
carry on.
yeah, so this gives like basically all of the life functions that our cells do. Like basically like when you're conceived, you start off with like some, like your mom and dad's DNA has like combined to form the DNA of you. But then in that instruction set is a way to create proteins, but then also to recreate or replicate itself. So you can now have cells like the initial zygote or whatever that you were as the under this like egg and sperm combination has the instruction set within that DNA to replicate itself. So that's also contained in the DNA, is how to read off certain instructions from the DNA and then replicate yourself. And then each of those can now do those functions as well. So you start to get this like multiplying organism. And basically all of that instruction was in the DNA at some point.
To begin with. So all of the instruction that is needed to build my full adult self is encoded in the zygote that I once was?
Yeah, like it
Wow.
needs to be actualized, but like the potential for it was there. But
Every
then
code was there already.
yeah. So your
Holy
DNA
shit.
is this ginormous strand of these letters that are like millions of, I don't even know the exact number. Like it's
Just
hundreds
a
of million.
specific code within a large...
Yeah, but it's not
number
like
of-
it's not like all of those millions are being read off at a time. It's like certain chunks of it, which are called genes, can be read off at times.
Right. To build you in the sequence that is needed.
And I believe it's also the case that like, so you know how the 3 letters code for each amino acid? Let's say the transcription process happened 1 letter to the right, and then it copies the same message from the same location on the DNA. So even if the message looks the same, if it just started 1 unit to the right, then you get this different chunking of 3
Completely
things
different.
and completely different proteins. And
Wow.
so you can
That's
have this.
how you can condense so much information.
Yeah,
in
you can
one-
have similar strands of the DNA coding different like functions with these proteins that are getting built.
So you can start to get a sense of how sophisticated this is when
Yeah.
just moving one character over
And
changes the whole
another cool thing is
sequence.
that, yeah, sorry I cut you off a bit, but another cool thing is that every cell in your body has the same DNA in it. It's just how that DNA is expressed in each cell is different. So let's say in my skin cells, certain strands of the DNA are exposed because the DNA likes to like coil itself up. But then based on the DNA's local environment called the epigenetic environment that exposes different strands to be accessible. So now you can access different strands and do different functions. So our skin cells have different strands exposed to getting transcribed compared to like our liver cells or other cells in our body. So you get this like differentiation of cell types, even though it's all the same DNA.
Based on the different environments that they're in?
Yeah, based on the different environments that the DNA's in.
So chemical environment or what?
Yeah, like the different proteins that are around the DNA dictate the chemical environment. Like maybe some proteins can like pull apart certain parts of the DNA and get access to different previously inaccessible parts and then start to read off there.
Cool.
Yeah. Again, I'm not an expert on this, but like,
no, it's still sick.
We'll study more for a full episode. And
are there any other parts of the cell that you haven't mentioned and that you know the function of?
Oh my gosh, there's so many other parts of the cell, but like I don't know enough about that to like just
too much to go off on. I like that you talked about DNA though.
Yeah.
In that whole process. It's fucking amazing. It's so miraculous.
We can get a molecular biologist on or something and they can teach us about this.
Yeah. I hope this is adding some appreciation to your life and how the sun is giving us what we need and the earth is perfect distance away from the sun and DNA is going through this crazy coding process to build proteins and essentially create us and who we are. It's fucking amazing, man. Next question. CERN particle accelerator. What's it for? How does it work?
Yeah. So CERN is, I believe it just like a name for the whole array of different accelerators and stuff. So like the accelerator itself is called the Large Hadron Collider. CERN is just like the location or the organization that does all, like there's many other experiments.
Sorry, like what collider?
The Large Hadron Collider.
Hadron, okay.
So I'll just say what a hadron is. It's basically a bundle of quarks. So you know what, I've described quark bundles to you before. Like a proton is a bundle of quarks. A neutron is also a bundle of quarks. Hadron is more general because hadrons also so protons and neutrons are bundles of 3 quarks, but then you can also get a bundle of 2 quarks, and those are called mesons, but those are more exotic. So like for our purposes, like just think of as hadrons as like protons. So the Large Hadron Collider is a large proton collider, which is like many kilometers in diameter. So
but
it's a big circle.
Hadrons, not just protons.
Well, it's colliding protons.
Only protons.
Yeah.
Okay.
But then it's producing. So the purpose of it is to smash these protons into one another. And when you have a high enough energy beam, it's like with the atmosphere that we were describing before. When you have a high energy proton smash into the atmosphere, it gives off a shower of particles. So with the particle accelerator at CERN, the LHC, it smashes these 2 beams of protons head on into each other. And then that gives off a shower of particles, of fundamental particles that the physicists want to study. So basically, it's allowing you to probe deeper into the nature of particle physics. The higher energy you can get those beams to be that are smashing into each other, like the smaller scales of reality you can get down to. So that allowed them to detect the Higgs boson.
Wow.
And verify that its existence. I believe they built the LHC because they wanted to test supersymmetry, which was a theory that people had throughout like the late 1900s, and like this theory made a lot of sense to people, that if we build the LHC, we can start to observe these more exotic particles. So with supersymmetry, from what I understand, it posits that for every particle we're used to, like electrons, protons, etc., there's a corresponding superparticle, which is like more massive and energetic, but it corresponds to like the same math or underlying reality of these particles. So they're like a symmetric particle, just at a higher energy scale. And they thought that if they could smash these energetic proton beams together, they could observe these more exotic particles, and that would verify their theories. But I believe they didn't find anything corresponding to that, and that really confused people. And a lot of people, I believe, also think that, oh, maybe we just like we didn't quite get the energy scale right. Like if we build an even bigger accelerator, we might still be able to find supersymmetric particles. But you need billions or trillions of dollars to build one of these accelerators, so it's kind of like hard for them to do that now. But they're still doing lots of experiments with the LHC and whatnot. So
how do they think that there's bigger symmetrical particles?
Oh, this
there?
comes out of the...
Don't you think they'd be able to see bigger ones? If their intent was to find something smaller, I could see that, but...
Oh, I don't mean... Yeah, like it's just... You need really high energy collision events to produce those particles for some short amount of time, that you would then detect them, and then you could then verify your predictions using that. But under normal circumstances, those particles aren't just like existing around that we can just observe them. So that's why you need to smash these beams together. But I believe they didn't find anything related to that. But they at least got like the Higgs boson as like a little side prize. They're like, okay, well, here's the big news of the Higgs, but
still,
which is still awesome, and they're still
valuable.
doing like cool science and stuff there. But I'm not sure what else like are the
Like,
big.
what else is there?
Yeah,
Are they still trying to find smaller fundamental particles with it?
I don't know. I think there's definitely like tons of experiments for them to still do, but I don't know if they're like actively, if there's any other like new particles that they're testing for at the moment. Yeah, it's been a while since I looked into like particle physics in much detail, but
okay, cool. Thank you. Next question. Can you give a scientific explanation detailing how microscopes and telescopes work?
yeah. So this is like a general field of physics called optics, which is basically the study of light, or how light interacts with matter. And then also how you can like manipulate light by engineering certain constructions of matter to manipulate the light in ways that are good for us. So like, for instance, in both of those microscopes and telescopes, there are lenses, which basically humans would manufacture because we know how light works. And this lens will give us a magnified image of something small or something very far away that we want to observe. So with optics, it's basically us. You can like write down math of optics, and like basically you can see that light travels approximately in straight lines, and then it interacts with matter in certain ways that we can then like bend the light and then refocus it to get a clearer image. So like the way to think of what a telescope or a microscope is doing is like, okay, pick an object like in your room. Like let's say there's like an apple in the distance over there. So if I'm in my position right now, I would look and I'd see the apple. But then I could walk a meter to the right and still see the apple. So what that means is that apple's giving off light in my initial direction, and also 1 meter to the right in that direction. And if I get a little creative, I'm like, okay, maybe what if I collect the light from my initial position and where I am now, and refocus that onto a point. So you're basically, with telescopes and microscopes, is you're collecting light from a wide range of angles or a wide range of, you're basically just collecting more light. So you're not just at one fixed position looking at an object. You're collecting the information from different locations and organizing that or refocusing that onto one point. So with the lens that you construct, it's like a circular lens. And let's say that's a microscope. Is that lens is looking at some tiny thing you want to look at. That tiny thing is shooting out light in all directions. But when it hits one end of your lens, like let's say the left side of the lens, then the way I've constructed the lens will focus that light back inwards to a point. And similarly for the right side of the lens, it's also focusing the light that hit the right side back to a common point. So I'm collecting all this light around the surface of the lens. That's all being refocused onto one common point. And according to how I've constructed the lens, you can then magnify those objects and see them in higher resolution than you could just like by your eye, for instance. So our eye also is operating with a lens.
Yeah, I was going to say.
And our muscles in our eye can contract, basically squeeze that lens to be like thicker and thinner to then organize light and basically look far away into the distance or like look at an object close up.
Well, because it's also like bifocal vision is doing this. Each eye is doing that, and then it brings the light together for a concentrated.
Yeah, and then that gives you your depth perception as well.
Oh, really?
Yeah, so
Bifocal vision gives us depth perception?
yeah, bifocal vision.
But I can see depths out of one eye or the other.
Not very well. That's
Not
kind
as
of like
well
an
as-
illusion of your brain. So your brain, like right now, you're thinking that you're able to see in
It
and
seems the
much
same to me
depth.
when I'm testing bifocal.
That's
to
because your
single eye.
brain's used to constructing with depth at this point.
Huh.
But if I got you to do some tasks, like if I held up something in front of you and you were like meant to reach out and grab that thing, you're not going to be as good at doing that if you don't have bifocal vision,
Wow.
because you won't be able to perceive the depth that basically comes about from like a triangulation of that object.
Right, that's cool. Okay,
Yeah.
this makes sense with microscopes and even bifocal vision, but for a telescope, if you're looking at Jupiter through a telescope and the fucking lens of the scope is only like the size of my hand making like a circle,
Mm-hmm.
how are you getting multiple angles of that light from this massive object way the fuck out there? Like, it makes sense when you're getting multiple angles of the light from a tiny ass microscope through this little lens, because the lens is way bigger than the subject of study. But when you're looking at a subject of study that's a massive planet in the distance that's way bigger than my fucking lens, how is it the same process?
Okay, so the object is way bigger, but the object itself, Jupiter, is massive, but it's a tiny little speck out in the sky.
Okay.
So it's not
So
like,
because there's distance, it's the same process as
Yeah.
the microscope.
so your telescope would also work if Jupiter was massive in front of you. It would just magnify some spot on Jupiter.
Right. I see what you're saying.
Yeah.
Okay.
Yeah. So you're basically collecting light from different directions that aren't accessible to any single point, and then that allows you to magnify that image.
Right. I guess
And-
in both situations it's magnification. So
Yeah.
okay. Cool.
Yeah. So optics gets super deep as well, but that's like the very basics of optics. Yeah.
Have you ever looked out of a telescope out into space?
Yeah. It's
Where
awesome.
at school?
At the observatory in Calgary.
What did you see?
I forget what we were looking at. I think it might have been like Jupiter or something, but
So it wasn't
can't
like
remember.
life changing. Like,
Oh, it was super cool. I just don't remember.
could you actually see like
Yeah.
the fucking like Jupiter as a planet? Like,
Yeah, yeah.
enlarged?
Depending on how good the telescope is, like you can see it quite clearly in like a really nice telescope.
So was
But
the one
in-
that you were looking through really nice?
Again, I don't.
It sounds
I don't
not
remember.
memorable enough to be
Yeah, again,
life-changing.
I don't remember. I think it was just some dude's telescope he'd set out. Like,
Okay.
in the-
God damn it! I wish you remembered.
No, I don't remember.
Okay. That would be sick. I want to have a fucking telescope pointed at space, a fancy one, someday.
When you're rich.
A fucking observatory. Okay. What is or are the most wild formulas in physics you've ever seen, and what are they explaining?
I guess the classic like favorite math equation for lots of people is the one that relates pi, the number e. So e is a number which is like 2.71 ... into infinity. So it's like it's 2.71 with a bunch of other decimals that go on forever. So that's the number e. And then there's the imaginary number, which is the square root of -1. Okay. So
Okay.
if you raise e to the power of the square root of -1 times pi, so e is the base, and then in the exponent is square root of -1, which
Yeah.
we also call I. So that's
Okay. E
so
to the
e
I.
to the I pi
Pi is where?
in
this
the
equation?
exponent. So
Oh,
it's
okay.
e to the I times
I
pi.
times pi. Okay. Yeah.
And then if you add 1 to that, you
Plus 1
Plus
to the
1.
whole shebang.
plus 1, that whole equation equals 0.
What the fuck?
So so like 2.7 to the power square root of -1 times 3.141 to infinity. If you do that itself equals -1. And then if you add 1, then it gives you 0. So that's like the most beautiful equation in math to lots
Why?
of people.
What's it telling us?
So that it gets quite deep, but it's just the fact that you're relating. So e, I, pi, 1, and 0 are all like, okay, 1 a bit is a bit less interesting, but 0 also was like some revolutionary number back in the day when people didn't have a concept of 0. So it's relating like 5 of the most powerful concepts in math, which are just different numbers in one equation. And that specifically that exponent term, the e to the I pi, is quite a beautiful result of mathematics, which is a bit in depth to explain, but it's it falls into what's called complex analysis, where for a long time, okay, let's say I give you the number 2 and you square that number. What is that?
4.
Okay, what if I give you -2 and I get you to square that number? So what is squaring? It's multiplying that number twice to itself.
Mhm.
So what's -2 times -2?
Do the negatives cancel out? And
Yeah,
that
exactly.
was +4?
Yeah, so for a long time,
It's been a long time since I've done
No,
that.
that's
but
okay.
I have to ask.
Nice,
these
yeah,
things.
that is right. So for a long time, mathematicians kind of just stopped there, where they're like, well, the square of any number is just a positive number.
Right.
So the square of any negative number is a positive number. The square of any positive number is a positive number.
Right.
But then they also defined the square root operation, which goes the other way. So if you square root a number, like let's say I tell you to square root 4.
2.
Yeah. But then they were kind of stuck where if someone like some snarky mathematician was probably like, well, tell me this, what happens if you square root -4? Mathematicians in the past would have just stopped there and be like, oh, that's nonsensical, you can't do that. Because the square root, you can only take the square root of a positive number. That's like what mathematicians like had insisted. They were just like, this must be the case. But that's an assumption that you make. You didn't have to make that. You can come up with what the consequences are of if you allow the square root of negative numbers to occur. So that's where this number I comes in, is the imaginary number, square root of -1. So basically you just say
what
like
the math would be.
Yeah, so you just follow the consequences of what the math would be, and it has all these nice properties of, actually, if we allow complex numbers in our mathematical equations that we're used to, it actually describes rotation extremely well.
Whoa.
So it's, in physics, you'll find this letter I everywhere, which is this imaginary number. And in quantum mechanics, you'll find I everywhere. You'll actually find e to the I times some number all over the place, because
I feel like I've seen that in like movies and shit.
Yeah, so that's describing like rotations, or basically periodic, something that's periodic. So, you know, like sine, like the sine and cos functions.
Yeah.
So, sine of theta is like describing like, anyways, this is getting too complex, but
no,
but
you can go there.
Okay, so
Just explain.
sine is a periodic function. That's a wave. Like, you know, a sine wave is a wave. Cosine is also a periodic function, which is also a wave.
A different type of wave, different shape. Or?
Yeah, it's the same shape, but it's just shifted compared to a sine wave. Sine and cosine, actually, people get introduced to them via triangles. But that's a bit misleading, because sine and cosine are actually describing circles or periodic things.
Fucking school, fucking pieces of shit.
So if you imagine a circle and you draw a line from the center of that circle to any point on the perimeter of the circle, so go from the center of the circle to any point, and then if you draw a line straight down, you can make like a triangle out of that. So that's where these triangles come about.
Oh, okay.
And then if you take the sine of that angle, you get the opposite side length. And if you take the cosine of that angle, you get the
bottom
adjacent side's length.
Okay, yeah.
So that's where like people are initially taught this in school, is trigonometry, which is teaching you how triangles and sine and cosine relate to one another. But that's pretty like vague and doesn't really mean anything. It's like, why am I studying triangles?
Right, yeah.
But then you start to realize that, okay, take that line that I've drawn out from the middle of the circle and let it rotate around the circle. So it goes from like the right end of the circle and starts to rotate around the circle. So that's some periodic function. And at all points, like let's say you let that thing rotate kind of like a clock, like the arm of a clock. If you stop that at any point, you can draw a triangle and calculate like the sine and cosine. And if you let that rotate out and then plot what the sine and cosine is at every point of its rotation, that perfectly draws you these nice sine and cosine waves. So you can start to see how these triangles, this circle, and these waves start to relate to each other. So you can start to like understand actually what's happening in the math. And then what is the case is that when you use complex numbers, which are using like this square root of -1, you don't have to write sine and cosine everywhere. You can just write like e to the I times some number, and that describes a rotation much more elegantly. And the math is very, very nice after making this transformation.
Sorry, what's E again?
E's it's called the natural number. There's very deep reasons for why it is what it is, but it's like 2.71 blah 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 decimals. And that describes exponential growth very naturally. So anytime you have exponential growth or exponential decay of like it's just a very useful number that naturally describes processes or exponentiality. The notion of exponentiality, it's like the natural number to do that process in.
Okay, cool.
And then pi is related to circles as well. So when I describe this circle with the rotating arm around it, if the angle is pi, you're at the -1 portion of the circle. And that's why, so e to the I times some angle tells me where I am on the circle. So if I go e to the I pi, I'm on the left side of the circle. And if the circle's radius is 1, then e to the I pi is at -1.
Sorry, radius is different than diameter.
Yeah, radius
How?
is the length of that clock arm. So if the clock arm's from 0 to the edge, and I like let it rotate around the circle, so e to the I times some angle will tell me where I'm at the circle. So e to the I times pi tells me I'm at the -1 point of the circle.
Okay.
And that's why when you add 1 to e to the I pi, you get 0.
Right.
There's much more we could say about this, and it's better with visuals, but that's more or less like my favorite formula, and like that's kind of like the cliche to say as like a mathematician or something. But
so the formula in its entirety is getting at like just a point on a circle.
Yeah.
How does that apply to reality? Like, why is it so useful and beautiful?
Yeah, so that equation itself is sort of just a byproduct of like what we've arrived at with this complex analysis. But then these e to the I theta functions, so theta is like the angle. So that describes the phase of quantum particles, for instance. So every quantum particle will have some phase attached to it. So if we start to describe quantum particles with these e to the I times some angle functions, we can start to describe quantum mechanics and quantum mechanical interactions very nicely and neatly.
Whoa.
If you basically look into any quantum theory, you'll see these e to the I thetas floating around all over the place, which is like the particle's phase. So you can do basically all your complex quantum calculations very nicely.
Two questions. So it requires theta to give it an angle to identify it as a quantum particle, because it has to do with where it is.
The theta is like what angle is this like quantum state in right now?
Right.
And it's less of like a physical angle and more of, so it gets very abstract. That's why it's like it's hard to get into the details without having like laid some more groundwork with quantum mechanics. But
okay, that's okay. We don't have to get into it yet.
Okay.
And then other question is, a quantum particle, would that be different than a subatomic particle?
No, all subatomic particles are
Quantum particles.
Quantum
Okay.
in nature, yeah.
Okay, sweet. Yeah, because it has a quantum number.
Yeah.
Which is the 4 different types of factors.
Yeah, there's
4
a
different
bunch of different
digits?
quantum numbers, yeah.
Okay.
Yeah.
Thank you, sir. Do you enjoy calculating for biology, chemical compounds, or engineering type of stuff more, and why?
I think engineering stuff more.
Because it's more applicable to what we see in our
Yeah, I
everyday
think
life?
I think so. It's more like tangible, and you can sort of understand how like objects move in space, and
Right.
how like you can start to build structures and work through math and stuff like that. But biology is interesting too.
Because we are still made of biology, but it's less seeable, I guess. It's too microscopic to really get a
Yeah.
like an everyday life type of observation on it.
Also with like explicit physics calculations that I can do by hand, it's much easier to describe like objects moving in space, or like gravitational orbits, or like structural integrity. It's much easier to describe that with the math I can write by hand than like biological systems, because the amount of complexity in a biological system is sort of beyond the equations I can solve by hand. Like people put those equations into computers and get the computers to solve it for them, but it's less direct computation in biology, I think.
Right. Would you see yourself being an engineer then at some
Yeah,
point? Or is
yeah.
that a whole different like realm of schooling you would need?
I could
does
probably
a lot of physics cover the courses in engineering?
Yeah, engineers like applied physics more or less.
Yeah.
It's like using physics knowledge to
To a specific field.
do useful things in the world. Yeah. So
I was gonna say, sorry, before you answer that, isn't physics applied math to reality?
Yeah, you could. I think you could say that. Yeah.
So physics is applied math, then engineering is applied physics? Like,
Yeah,
interesting.
because like physics is not inherently trying to build things. You're more or less trying to describe what nature's doing with math. And
So
then-
yeah, and then once you know what nature's doing with math, then you can apply it to a specific field.
Yeah.
Okay, cool.
and you can apply that and build a bridge or build a car or whatever.
Nice. So sorry, go on and
Yeah, I could definitely see myself doing an engineering job as like after this.
sick.
Would depend more on like what the field is. Like it would have to be interesting.
Do you
Yeah,
think
I
there's a field right now that you already qualify for without needing more schooling?
Probably. I think like lots of computer-based stuff, like AI engineers and whatnot.
But I thought you were more interested in like the external world stuff than computer.
Yeah, I think I still am. But I think at the end of the day, my job will still involve like computers and probably some portion of AI. So it's like, yeah, there's a lot of overlap once you like get a base knowledge of science and stuff.
Do you want to jump on the AI train because of the potential with it of new discoveries, and you think that's fascinating?
Yeah, I think I'm interested in it in a couple levels, like in the like basically just the realm of possibilities it can unlock for us. I'm less interested in like the systems themselves, like the AI like, algorithm and whatnot. Because at the end of the day, all the math is sort of like just calculus and linear algebra. So like the math itself isn't very interesting, but like the applications of it are super interesting.
Definitely, yeah.
So I don't know if I'll go into like a field where I'm improving AI systems, but sort of using the intelligence from them to solve other cool problems would be cool.
Totally, it's like using ChatGPT
Yeah.
to applied field. So yeah, like things where it can be applied, like what you said with the mapping of DNA strands to become 3D. What did you call that?
Protein folding, like
Protein folding,
alpha
yeah.
fold. Yeah.
How AI discovered that alpha folding.
It discovered the mapping. Yeah.
The mapping, yeah.
Yeah.
So it could be applied to things like that, and that's
Yeah.
what you'd be interested in.
Yeah, that's super cool.
Yeah.
Or like, I don't know, using AI to like solve games has been cool, but most of the cool games to be like chess and Go have been solved more or less with AI already. But there's other cool applications of AI that you can use to solve things. It'd be cool to like see if you could get it to solve different realms of physics or something. But
Yeah. But that kind of goes more towards the programming of the algorithm also to figure that stuff out.
Yeah. But if it's like
It's kind of both that you need it.
Yeah, if I'm
for.
trying to improve it to then solve other cool problems, then that's all right too.
Yeah. Seems like regardless, yeah, you would need to do some tinkering of the algorithm.
Yeah.
Cool. Another physics or math question. What the fuck is calculus? Google says it's the mathematical study of change. Why does the world make it seem harder than geometry and algebra? Is it because it encompasses all aspects of math?
Yeah, I'd say calculus isn't as hard as maybe the world makes it seem to be, in the sense that the math itself, at least when you're learning it, isn't anything like more difficult than like learning algebra or learning geometry. Like you just have to learn certain rules and certain ways of thinking about it. But then there's often like shortcuts and like easy mathematical tricks you can do with calculus to solve the problems you're trying to solve. But like one way you can think of it as being more complex is that like algebra is like a static thing on a piece of paper, which is like these equations that I can then manipulate and stuff. And it's describing something, like something potentially static. But like again, algebra is quite general because it's like a tool that I'm using to solve calculus as well. So like for instance, geometry is like the study of these shapes. And if I'm just looking at triangles and like circles and stuff, like those are pretty simple shapes, but then geometry can also get incredibly complicated when you go into like higher dimensional spaces, or like topology, which is like the study of like surfaces and manifolds, and like it gets like each of those fields can get so complex. So it's kind of dumb to say that calculus is like much harder or something, but the sense where it is maybe trickier on like first order is that now you're looking at how things change with respect to other things.
So it encompasses all those different fields of math and just talks about the change of it all.
Kind of, yeah. So calculus, you're more or less looking at how one variable will change with respect to another thing. The most direct way to think of that is things changing in time. So calculus is helping you describe the dynamics of things in the world in time. So if you look at other fields of math, it kind of all stops time, and you're just like looking at my equations at this point in time.
Right.
But calculus is like, well, what if this particle moves over here?
Right.
And then the particle doesn't just move like in a blocky way where like it moves from 0 to 1 second to 2 seconds in like straight lines. Like it has moved a little bit at each millisecond.
Yeah.
And then if you zoom into each millisecond, it's like, oh, it's actually moved a little bit at each nanosecond. So like calculus is basically looking at
applying time to math.
Yeah, it's applying the like time, or basically like infinitesimal changes of something with respect to something else.
Okay, sick.
So like with a particle, for instance, let's say I have a charged particle moving. If there's no forces on it, it'll just move in a straight line, and I can describe that very easily. But most often you need what's called a differential equation, which basically that equation stores the information of how that particle will change in time in response to like other external forces, for instance. So like with the charged particle, let's say it's moving, but then there's other charged particles around. I need to keep track of where all of those other particles are at every instant in time, because depending on where they are, that changes the force on my particle right now. So you start to get into like this really complex dynamical process.
Is one large formula, or is it many different formulas typically being done to then figure out your original one?
In general, you can write down a very short differential equation. So for instance, with electromagnetism or electrodynamics, so dynamic means changing in time. If you look up Maxwell's equations, there are 4 short equations, which in principle contain all of the information about electrodynamics. But contained in those equations are terms that describe the charge distribution and how charges are moving as well, which are called currents. So if you look up the Maxwell equations, you'll see like this little P letter, which is a Greek letter called rho. And then you'll see the letter J. And both of those contain information about all the charges around you in space. And as well, the J is all the currents around you in space. But in principle, those 4 differential equations contain all the information you need to know for how things will behave in this arrangement of charges and currents and whatnot.
Cool.
And same with Einstein's equations for general relativity. You have a quite a short equation with Einstein's equations, but contained in each term are many other terms, so it's kind of just like collapsed into one short equation. So yeah, in that case, it gets more complex. You get like 16 paired differential equations. And once you get pairing between differential equations, that's basically saying that like if one thing changes up here, you need to keep track of it down here at the same time, because now shit's different.
Right.
And you need to, and then it starts getting really complex, and you typically can't solve these differential equations with algebra. Like very simple ones you can solve on a piece of paper, and that's what they'll get you to do in a calculus class. But a lot of the times it's like intractable to actually solve these differential equations. And by solve a differential equation, I mean it, like the solution to the differential equation will tell me that particle's motion at all points in time, for instance. Like let's say I drop a particle, like a charged particle in a field of other charged particles, and I just let it go. The solution to that to all the differential equations is that charged particle's path as a function of time.
Okay.
So that's what I'm trying to solve for. But often getting that solution is impossible by paper. You often need to like run it through a computer to keep track of the particle itself, but also like
at each phase,
the distribution at each point in time.
Right.
And you let your computer chunk away and solve like the motions and stuff.
Cool.
So calculus in general is the description of change. But it doesn't have to just be the change with something as a function of time. It can be the change of something as a function of something else. So as something else changes, how does this one thing change? So you can get into like stocks and finance.
Wow.
You can get into many other realms of science or just like pure mathematics and stuff. So calculus is like pretty general in that sense, where it's just like if something's changing as a function of something else, like oftentimes you'll use calculus to solve.
Okay, sick. That's a very good explanation. Thank you. And then next question, what are the most leading edge things being discovered or improved by science right now worldwide, in your opinion? And would you like to speak to any of them in particular?
I think the obvious one is like AI research.
Do you want to go off on that shit? Or did we already a little bit?
I could go off. I feel like we should have an episode on it as well, but yeah, just like learning how to create intelligent systems. So like intelligence can kind of broadly be defined as as like the ability to solve problems. And us humans have a type of intelligence where we're intelligent in many aspects, but less intelligent in other aspects. So like a computer is way more intelligent at running computations very fast, but they're much dumber in like being able to like tie a shoe or something. So like we have general intelligence as humans, but at the moment these artificial intelligences we make are not good at general things. They're quite good at certain
specific
applications.
Yeah.
So like trying to create artificial general intelligence is a huge thing people are trying.
Do you think it's attainable?
I think so. I don't
to
think,
a human capacity?
Yeah, I think that's where we're going to have to confront our humanity at some point soon, because it's like we'll have to kind of figure out what makes us human. Like, is there some essence to us that is fundamentally different from where a machine could be? Or is it in principle possible for machines to attain a similar like intelligent life? Maybe not conscious life, like that's another argument, but like at least
The intelligence on the same level
side, like the
in terms of general
problem solving abilities.
Yeah.
And even if you don't quite get there, it's like, okay, what can we use these intelligent systems to help us with that we would have never been able to solve on our own?
Right. Obviously, there will be improvement, but I don't know if I believe that it'll ever get to our level of general intelligence. Maybe because, okay, like, what's your opinion on what Federico Fagin said about our reality and computers being coded with binary, but the human consciousness being coded with quantum bits?
I think that's a good train of thought, but then it also doesn't necessitate that we are fundamentally different. Like, because then in theory we could build quantum computers that behave similarly to us.
In theory, but we haven't been able to do it.
No, I mean, but again, we've only been technologically advanced for like 1,000 years, not even like
less
scientifically advanced for like 300 years, 400 years. So it's like
we're infants still.
I think we're little baby boys and girls, and we've got a lot of but we've got a lot of potential room to explore this space in, if we don't kill ourselves before we do that.
That algae, man, I'm telling you. Algae crisis 2058. Okay. Are there any other fields of science other than AI that are worth bringing up that are interesting to you?
I mean, because
everything's always being discovered and improved. Like, it's kind of a silly question. We could talk about this for hours, but
yeah, there's a ton that's interesting. But I think the fact that there's so many, and it'd take too much to go in depth. Like
quantum computing, you brought
material
up too,
science, quantum computing, fusion, space travel. I don't know.
Okay.
Yeah.
We should do a episode on the shit that I've heard that is possible, like spiritually and just in the universe, and see if you can maybe make sense of it scientifically. That'd be cool to cook up.
Sounds good.
Okay, so last question. We know you agree with Feynman about atoms being the most important scientific discovery, but what are the other main discoveries that we benefit from, and how do we benefit from them? I'm guessing relativity, quantum mechanics, etc., but is there anything else other than those?
Yeah, it depends what you define as benefit, I guess. I think understanding atoms and how they actually operate gives you so much power over like our accessible world, because the world we interact with is like
Atoms
built up of atoms, more or less. Like if we wanted to travel through wormholes or something potentially, then it's good to know like general relativity or theories beyond that, like whatever, if string theory is real or like other big cosmological theories. But and to know, to understand atoms, like in that episode I got, that's still very like basic level.
Oh
So,
yeah,
like,
we should go deeper.
Going deeper into like actually understanding quantum mechanics can allow you to do basically everything atoms do, and then you can kind of build up from there, like build into like starting to understand chemical systems, biological systems from the ground up with this like atomic notion of reality. Understanding atoms also helps you engineer materials, so like you can build semiconductors and then build transistors and then build computers and then build artificial intelligence just from understanding like principles of atomic theory and like quantum mechanics. So
quantum mechanics underlies atomic theory though.
Yeah.
So are you saying quantum theory is not necessarily necessary to discover all the things that atomic theory has brought us?
It's not necessary for a lot of things. Like you don't need to understand how your stomach processes food to get the energy from like or I don't need to understand how my bowels take a shit to be able to take a shit. Like I'm a level separated above it.
Meta shitting.
Yeah. So I'm a level above the requisite knowledge to do the functions. So what I'm getting at is that if I just think of there being little balls, like little billiard balls around, and thinking how those billiard balls interact with one another, I can do a lot of useful science without having to know that there's quantum mechanics underlying it. And that was done for like 100 years before quantum mechanics was ever solved. But you definitely unlock way
Another
more
layer.
freedom and actual like utility from knowing the quantum mechanics, because then you can start to do way more complex like material science, and you can understand why like semiconductors and transistors work, and then like extrapolate from there and stuff like that.
Right, it's true. Yeah, it seems like obviously with every discovery of a new layer of things, it unlocks a whole new set of things to be discovered.
Yeah.
Like when you and I are going to win a Nobel Prize for discovering how consciousness works, and we get the extra special privileges that'll bring.
Yeah.
And yeah, it'll be fun times. Any last minute general scientific things that
No, I think we got lots of time in the future to get into all sorts of cool, more in-depth topics and whatnot. So for now, I'm happy.
Okay. Thanks, guys, for joining us. I hope you learned something. I sure did. Happy to have Jordan as the co-host on this, bringing the brains to this fucking shebang. And yeah, hope you guys enjoyed.
Bye.